Okay, so I am a beginner. It's been interesting, but if I could take digital forensics, maybe I will look into having a late night around digital forensics. So, as I was still introducing myself, I work in the security industry locally. I have mentored, trained, guided, and supported so many different people over the time that I've been there. And it's basically a very beautiful thing to have new faces, new young people trying to break through in the industry. And one of the things I would probably say is there can never be enough security professionals, so you guys should put in the work and ensure that, yeah, you can be able to shoot because everyone's talking about security, but very few people are doing it. So we're happy to have you guys here. Kindly confirm when you can see my screen so that we can start. Okay, so I have a 6-page slide. Basically, it's very simple, not so not so scary, but when you guys can confirm you can see, then we can start. So the biggest question I'm going to ask is, what is reverse engineering? And yeah, um, this is a discussion. To me, I don't personally, I don't teach classes as like it's some form of weird knowledge transfer. It's basically a discussion to understand and also better engage from the training point of view. But when you ask to introduce reverse engineering, um, we need to first understand the concept around what we call forward engineering. And forward engineering is basically, guys, save our mics, save our mics for upload and other things. So forward engineering is basically the context around how we build programs. And majorly when it comes to reverse engineering in the context of where we're trying to run, we are looking at being able to understand the design process of systems, the coding bit around implementation of design, and then compilation, and then of course assembly to build out whatever executable we're looking at the end. And of course, when it comes to specific application design or um, like for example binary setup or things like that, when you're creating different executables, there are different, depending on the technology stack, there are different ways, of course, we implement this, but the whole idea comes to assembly at the end. And most of the different programming languages all go towards the end. And some of them, of course, take the workload around basically the compilation process, but the output is basically what we're looking at. So when you're looking at, of course, forward engineering, you first of all want to understand uh, when you have a design, you have to, of course, plan around it. You have to implement it in a specific way. You choose the algorithms you want. Maybe, for example, if I was saying that I want to, I have a specific routine that I'm building. Maybe say I want to become an effective person. I would probably say I wake up in the morning. I need to, I need to, I need to lay my bed, maybe have a cold shower, do this, do this. Those are different steps basically that build up a specific process. Then I have to, of course, maybe like get my calendar, put in those different time frames, and basically that becomes how basically I'll be running my life. Then someone will probably be understanding, okay, at this point, maybe every specific time X you at this point, every time X you at this point, every time X you're probably at this other point. The person is basically just trying to understand your process, and basically also around the engineering bit, reverse engineering bit, most of it looks at one. You have to be able to understand what you're going to be working backwards against. So when you look at forward engineering, it's basically how we build applications, how we work normally towards the different processes that lead to the final applications we have, the final code that we have, maybe systems that we're looking at, the mobile applications that are being built, web applications, all these different applications that probably you're going to be, in this case, working against. So the whole idea around reverse engineering is to understand this the functionality of a specific application in the case where we're working with, or mobile application, to understand its functionality so that you can work backwards to think around what the developer was intending to implement, and in that way it can generate for you techniques that you can go about finding ways, loopholes, to go around specific implementations of specific code logic or design or anything, because it's the same process around how most of the bugs at a low level are found. So when when you're basically how far are we, guys? First of all, because this is a 6 slide presentation, we're on slide 2 before we can get into the chaos. So I don't like over explaining, but I'm going to try. So what is lost in the transition between design and code? Yeah, there is so much stuff that we basically uh, lose when we're designing. For example, someone will have a plan of a house that has like multiple things. Let's look at, for example, all the plans the architectural plans that we look at that have been normally shared with us, like I don't know, harms projects, all those interesting things. You find that there is a detailed project having so many. You can even see tiny windows, beautiful grass, and all that. But at the output, we find that, of course, there is so much stuff that is omitted, and basically, this is also what happens at when we are doing most of these designs. For example, when you when you write your code, when you go into like compilation and all those things, when the code goes to a low level, if you're trying to maybe like achieve optimization and all those things, there is a lot of stuff that gets stripped out. For example, we have comments, variable names, function names, depending on basically how you want to what how you compile those that code. So sometimes you find that even algorithms are basically omitted. You find that you write your logic saying that, maybe say I want x should be if x plus, maybe say x plus 2 should be equals to y. But then at a low level, you're going to, of course, be interacting with like registers, and there is going to be a lot of memory memory read and memory writes to the different registers. That's going to be carrying this different data. So when you actually go low level, you'll not be seeing your your code syntax as easy. You'll now be probably looking at assembler and be working with registers. And that is basically how we lose a lot of information when we're going through these processes. So that is basically what happens even at a code level, even during most of the projects probably that you understand. So that majorly comes around different things. So when we look at, for example, when we look at the forward engineering tools, because guys, we're understanding the forward engineering process. We of course have like Vim or an IDE. You have these different IDEs that we have. Those are the ones that we use, of course, for building, writing our code. We have GCC, which is basically a compiler. Then we have things like strings, which is a utility for extracting basically human readable strings, or in this case, yeah, from like binaries. And then we also have strip, basically, which is used for optimization. That is to remove different of course, as you can see in the previous things, different data, like for example, the variables, functions, those things. Strip can be able to actually ensure that you reduce the size of your binary to have it in a small environment. So after understanding the forward engineering process, then you understand that every step in this, like for example, when we're reverse engineering, we're just going to be working backwards. We're going to be disassembling, decompiling, trying to understand, which is basically critical thinking, breakdown. Sometimes the process is tedious, and basically that is how we come up with reverse engineering. So I don't know whether that explanation has been good enough, but you guys can maybe help me ask questions at this point, because that is that is where my presentation ends. Yeah. Any questions at this point, guys? I'm just seeing fingers. Oh, nice. Thank you. So so when we are basically understanding reverse engineering, um, there are simple things that probably we need to understand. Um, I remember when we used to have when we used to have when we used to have when we used to do math, we would be given questions like x plus y, like maybe say x plus 3 equals maybe say 5, right? Something like that. Logically, they would give you something like x plus x plus 3 equals y, and then they'll tell you to find um, to find x, right? I don't know whether we guys studied in the same schools. So, but yeah, there would be those weird questions that would be asked of children, and in your head you'd be like, like, how do I understand? How do I find x, right? Then you'd go through the logic. You take, you of course do a minus 3 on the x side, on the left side, and then you find that x equals to 2. Correct? I think we all had this kind of thinking. Yeah, we all had this kind of, this was things they were teaching us in primary school when we were breaking down. So at computational level, we have, of course, what we look at as different operators also that help us achieve different logic. We have, I don't know how many of us, do we all have a background? How many of us are doing computing right now? You're all in university, so you're probably thinking you guys are doing engineering, software engineering. Yeah, you guys will forgive me. I didn't study those big names, but trying. So in all this, we of course have to understand that there are some things that we look at as. Let me try and use my friend Google. Uh, you probably, I don't know whether you heard of XOR. So if we have of course different. I don't know how we probably call them in this case, like logical operators. And if we have heard of maybe XOR, XNOR. The reason why I bring XOR as a very specific thing is because it's one of the, ideally I would say, uh, operators that you probably need to understand at a low level, because most of the algorithms that you'll probably be working with when you're reverse engineering will have either a component of XOR when you're moving forward, or XNOR, and these are basically the things that you would need to understand. So I don't know how. Let me just confirm this. I can't see my screen. Confirm when you can see my screen. Yeah. So there are some of these are some of the things that you probably need to understand from a baseline, like how is XO. I'm going to give you guys also just a book to read. Just guys, just please do remind me after towards the end. I need to give you guys a book on cryptography and basically the main things around understanding most of this, because the time that we have, which is 1 hour, is not enough to break down most of these things. But from my experience over time, security is not something that I can teach you. Like, for example, I come and tell you, I'm going to teach you reverse engineering in 1 day. I'm going to be lying to you. And if you believe me, then you also be lying to yourself. So the basic thing is to first of all understand the principles around how you actually attack problems, how you create a mindset that allows you to be able to face any problem head on, that allows you to be able to understand the tools that you need depending on the technology you use, because different there are different tools basically that are built for different things. And when you come, for example, to the x86 architecture, which is also one of the most interesting things that you probably need to start with, you will need to, of course, you have to understand how your general purpose registers are used, and now that's how we go deep into the reverse engineering. So the most basic example of reverse linear that I just showed you was, for example, if you have x plus 3 and you have equals to it being equals to 5, and I'm asking you to find x. Basically, if you realize that this is you working backwards, this is a very simple explanation to a loop, and you'd probably understand that, okay, this was us working backwards to actually find the value of x. So with the different using different operators operate in different ways. So for example, if we're using like the XOR is basically an operator that looks at, and guys, remember, everything we're working with is at a binary level. So that's why, of course, we have our zeros and ones, and yeah. So for example, when I'm studying XOR and I'm having A and B, and basically Q as my output, and XOR basically just looks at, if we have a 0 and a 0, this will definitely give me a 0. And if where I have a 0 and a 1, I'm definitely going to have a 1, and this is the same. And then when I have a 1 and 1, it gives me a 0. So two similar numbers will definitely give me the opposite, a 0. You get it? So if you have, like, for example, a 0 and another number, then you're probably going to have the other number basically as your value. So how would that probably turn out? It's been a while. I don't know whether it's like, for example, if I say it, let me say if I have 7, 7, what? Okay, if I have 7, this case 7 is basically just 111 in binary, and maybe say I had binary, maybe say 6 in this case. You can see I have 111 and 110. So if I was to say, for example, being 7, so let me just say bin 7x6. You're basically saying this is an equivalent of 001, right? So where we have 1 and a 1, we're basically going to get a 0. When we have a 1 and a 1, we're going to get a 0, and then we have a 1 and 0, we're going to get a 1. So this is basically just how XOR, and this is, of course, in Python, this is the operator for XOR, and this is how you probably understand generally how XOR is basically used. So this is basically just a simple explanation around it. So for example, if I had 100 and maybe say I XOR it, maybe say with 3, with 4 in this case, I'll have 96. But also when I XOR, for example, 96, guys, I hope we're together, because this is a very simple thing, but it's going to cost us. So when I XOR another 100 with 4, I get 96. When I XOR 96 with 4, I get 100. And if I was to XOR 96 and 100, I'm going to get a 4. So it's just basically something that transcribing messages, I can give full attention. Sorry, thank you, Karamagi. Yeah, hold on the logic, Moses. Please zoom out in the terminal. Okay, thank you, guys. Okay, I think that works. So this is basically just how we probably understand how XO works. Is that big enough, Sharon? So this is basically just, it's a very simple thing to understand, but in reverse engineering, it's very important normally when you go to the algorithm level to understand that if I see an XOR, for whatever input I XOR a value with and I get the output, if I did the reverse, I'll get the output, which was basically, I'll get the input, which was provided to XOR whichever value that is have. So this is basically 101 in computing, and I would expect that maybe you guys would probably understand it at this level. So another thing that we'll probably look at is the 86 error purpose registers. So when we're looking at, of course, maybe just a breakdown of, of registers. I'm sorry, but yes, I didn't really take so much time to prepare for this because I know that this is public knowledge, and there's some things I think that we're supposed to work on. We'll definitely be starting them in the next 10 minutes. So when we start with x86 registers, what are we talking about when we talk about registers? These are, of course, like this is the lowest level of like for example, okay, there are lower levels, but this is how basically we communicate with our CPU. So we have, of course, different registers that are built for different things, and the breakdown basically comes around what we look at as general purpose registers, uh, the segment registers. This one's basically just like carry. They have like carry flags on them, and then we have, of course, the pointers. So we have these ones: EX, ESI, EDI, EBP, EIPSP. These ones at the x64 architecture level. These ones, of course, will become bigger in size, and you, of course, now having the RSI, RDI, RBP. Those are the things that you probably look at. But what one of the registers you need to pay attention to is your EIP, because it's the one that basically points to where our code is going to be looking at a low level. So with this introduction mainly, I want us to more be hands-on, so that, can you move the terminal to the second workspace? It's hard to see given that it's transparent and it's white. Okay. Thank you, TE. Maybe, I don't know. I have no idea what I'm doing, but was appearance, transparency. Okay. I don't know what you've done. You made me do. Okay, is that better? Yeah. Thank you, T. Okay, so that's majorly just a small introduction to how you probably understand it and look at. And these are the things I'm going to explain, because we have the ear. We have, of course, you have to pay attention to, first of all, these register, these index, and these pointers basically, because they're the ones that are used for building the stack. So there's something that we call the stack, there's something called the heap, but as I said, this is introduction, and we'll definitely need more time to break it down. But I think as I'll provide you with material to look into it, you'll probably also, of course, you have to explore. For me, I believe, as I told you, one of the things I said with security, it's you have to basically be uh, self. I don't know what they call it. What's that word? You have to be able to push yourself to learn, because there are things that I would probably learn from you guys as I come into maybe to tutor next time or another time. I would probably get a new trick from one of you guys in the class because you put in the work and learn. So I explore, and I encourage you guys to be able to take on some of these these things that we are. Man, English is not my strongest suit, like, but yeah, I really appreciate the self drive. Yeah. So breaking down what we have today, uh, we are going to be basically looking at just a simple thing. I have a small file here, and normally when we are looking at understanding binaries, in this case, we're going to be very specific. Just firstly, before we dive down, guys, how are you guys at this point? Because I don't want to feel like, because I don't want to feel like we're going into zombie mode. Very good. Yeah. They told me that you guys are very good. So yeah. So when we are of course going through different challenges in life, when you have a problem, the first thing, of course, you need to understand is you need to be able to understand what you're working with, right? You have to breathe in. So this is the moment to like breathe in. So we have utilities like file that, of course, basically help us understand what we're working with. And if we're looking at this, we have something called an ELF 64-bit LSB executable. Normally, one of you guys, I know probably nowadays you're in the era where you can just copy this and drop it on Copilot and be able to get some knowledge around how it's built. But of course, this basically just gives you the name, describes the type of executable it is. You also look at how it's linked in terms of how it is linked, and then also look at where the interpreter is basically, what kind of interpreter it has, and then of course the build and the share. So, and you can see here that it's not what? It's not stripped. So when we're talking about on our 6 slide Excel, we're basically looking at forward engineering tools, and we're looking at strip as one of the utilities that we're using to, like, of course, build programs and strip them. So strip basically removes that data that basically we had in terms of the variables, those function names. It's like what we would look at as like, do you guys understand what obfuscators do? Yeah. So it's basically like how an obfuscator would work. It would basically remove like human readable syntax and leave there, for example, things that only the computer will probably understand. So we understand that this is not stripped. And yeah, we have tools like this. We have tools like Radea that basically can also help us understand and break down the structure of our file. So this tool basically is a very small Linux tool. I don't know whether you guys have heard of what to call R2. R2 is just an advanced command line hexadecimal editor, dissembler, stroke debugger. This is what we call Radea, and it's basically used for decompilation. It has other utilities around it, Rabin, so much. It has a whole community. Actually, this is, you can see, it has a full community that runs around it right there. And yeah, if you're definitely interested, you can also dig in to understand how to automate some of the tasks you'll be doing right there. So Rabin basically can be used to understand, for example, the architecture. We can ask for information about the architecture. We can see an x86 architecture, we can see an ELF. It has a stack canary. These are, of course, when we come to binary analysis around, we can be able to learn the importance of some of these implementations in terms of security. Then we're looking at the compiler in this case. If you remember, when we look at the forward engineering, we're looking at JCC as a forward engineering tool. It's also basically mentioned here as a compiler that was used for compiling this binary. Then we can look at Indianness, and then of course we also can confirm that it have code, and then those are like you also look at position independent code is true, and then also the OS is Linux. So these are basically the things you look at. Also stripping, and these are most of the things that probably will help you understand how the process of building the binary was basically done. So in this case, we have our simple encrypt file. We've been able to look at it. It's this. So if you remember, like my methodology normally around, for example, reverse engineering binaries, I first go by maybe analyzing, looking for, since we said it's not stripped, we can read through, we can go and use strings to be able to understand maybe what is exactly human readable at and what can we see from there. So we can see that there is, of course, if we remember this, when we're looking at files, we're able to see the interpreter, then we're able to see one of the libraries. This is a shared object. Then we're looking at, of course, the different functions which are being used: srand, fopen, ftail, time. Then we're looking at stack check failure. This is, of course, canary checks. Then we have seek. These are all different functions that are being called within the binary. So up to this point, I think we're together. We also have a glibc version that is news, and of course we can see now things like flag encrypt. Then we're seeing, of course, Ubuntu, and then we're seeing like CRT stuff. See, so if you're looking at all this, you're of course looking at different headers of like symbols that are being being uh, being broken down for you. But one of the core things that you probably need to understand is that when you're when you're looking at binaries, allow me share my other screen. Just when you're looking at binaries, shit. Okay. So when you're looking at when you're looking at binaries, you need to understand that it contains a program and its data, and of course, we were able to see what we look at as our interpreter, and this, of course, this is the library that defines how you load the ELF into memory. So whatever, when you have a program, you just have a program as a file. But once you load it, it's going to be, of course, taken up into memory, and that's now how we start the execution. And that is basically now where we'll be looking at it. So when we're looking at defining the sections within an ELF, in this case, we need to understand that there are some important sections that we look at. The .txt basically gives us the executable code. Then we have, of course, PLT and GOT. As you can see, they're also basically used to make, of course, library calls. Then we have data that, of course, contains our global writable data. Then we have oral data, and then the BSS. So those are like the important sections when you're looking at understanding what an ELF, or in this case, the binary, does. So you need to understand that these are structured files, and depending on how it's implemented, you look for specific data within specific sections, on the within specific sections, to find different things that you're looking for when you're trying to, of course, reverse engineer your binary. So there's things that, of course, are called symbols. Symbols, in this case, we're looking at, for example, like libraries, functions. These are all how you probably look at. And an ELF, depending on its structure, I think even when you, next time when you get a chance, maybe we can look at also maybe the PE structure. But in this case, we have this is how our ELF structure is. We have, of course, our sections, and then we have our arrow data, basically a simple breakdown of what we're looking at initially. Then, of course, we also now have to understand that if we want to work with our ELF, there are different ways you can look at. This is, of course, what we had used for compilation. Just a minute. I think I went. Yeah, this is what we use for compilation. We use binaries like read ELF to pass the ELF header. We can use object dump to, of course, also read the ELF headers. In this case, what we're looking at, and then also disassemble the source code. Then we can use NM to view symbols. We have patch ELF to, of course, manipulate the ELF if we want to change specific logic, application logic, or program logic in this case, since it's not like a full ELF. Then we also, of course, have object copy to be able to extract specific sections in ELF. Then remember, as I talked about, strip basically is something that you can use to to remove the information. So that's maybe just a breakdown of how to look at understanding how the structure of ELF is. So when you have, like, for example, when you go back to the utilities that we just mentioned, guys, I don't know, can you guys just give me a second, if you don't mind? Hello, Mark.
Morning.
I'm okay, morning. What's up?
The ATM that have gone off again.
All the ATMs?
Yeah.
Okay.
If you ask me to check on you, if anything that changed.
Just if I've made any change?
Is anything that changed?
No, not from yesterday. Not from yesterday. And I'm in the middle of class, so is it okay if I organize you and I call you back?
Okay, no problem.
Okay. Guys, sorry about that. Okay, where were we? Anyone to remind me where we were? So yeah, so we're looking at the structure of the ELF. I think you guys have all gone quiet, which is very scary because we're not even done anything yet. So if you remember, when we're breaking down the structure, we had arrow data, we had text. These are the PLT. These are basically things that you would look at. BSS data. These are different sections that you would see and expect. But of course, for example, if we start using the different utilities that basically I just shared, you find that some of these symbols can definitely, some of these things will start disappearing. So normally, since we're working with the Linux, we're working with Linux, and you can see some of these things like C. We expect that, for example, these functions, this basically was written in C. And yeah, let's get into the chaos. Let's get into the chaos and see how far we can go. So normally, whenever you get the binary, the first things, of course, you do is you look at checking for strings. As I said, you're trying to understand that. You're trying to maybe do recon, understand what the file does, and you're looking at how the interpreter is looking like. You're looking at maybe the things like, of course, remember how we had this read elf as one of the utilities that we're using. So read elf basically just does for you. It shows this is the usage options and then the file. So for example, if you had like read elf is used to read the headers, if you remember. And when you look, this is of course now how it starts to read your binary. You're supposed to understand that, okay, this is the actual structure of the binary, and it breaks down almost all the things that we're looking at. So you can be specific to what area of the binary you exactly want, you're targeting, what section you're targeting. So you can look at this. We're able to confirm, for example, this is our elf header. We're able to look at the magic number. Basically, I think you guys understand what magic numbers are. This basically just shows the format in terms of the file structure. Because remember, the elves are what? Are structured files. And of course, you look at the number of section headers. Then, yeah, it starts to break down for you the offset where a specific header is sitting. And yeah, this is basically things that you probably take note in when you're going deep into like forensics and all those things. So basically, those are the utilities that we're using to understand. So to dive deep into our program, because we have only about 20 minutes left since we started late, when we have a very interesting program in this case that's basically called file encrypt, and when we try to run it, it basically gives us what we call a segmentation fault. And if we understand what segmentation faults are, these are basically like errors during execution, and you probably need to understand why it's happening. So there are some utilities, for example. Um, well, Alice, I think Joel can maybe give a highlight to that because I was in for 1 hour, and yeah, I will align with the team. Okay. So so is Isaac on call? Okay. Okay. So so when we're looking at, of course, we're looking at segmentation faults. We can use utilities like ltrace. We can use strace depending on exactly what we want to trace. You can see here, this is basically just a library called tracer, and this helps you understand, for example, what libraries are being called. And with it, if we're to run, like for example, ltrace and the binary, in this case, we're looking at, there's something called ltrace, but we are seeing there is a function that is opened and it's looking for something called flag, right? It's looking for something called flag, and we don't have this within our file. So if I'm to say, for example, let me just copy flag.encrypt, that's flag 101. Let me remove flag.encrypt. So in our file right now, let me just encrypt 101 just to ensure that. So if I was to run encrypt, we're having segmentation flag. If I say this is a dummy test, then I'm maybe piping this into something called flag, what our file was looking for. Now, if you notice, we have our right. We have of course we have our flag, the new thing that we created called flag. And if we were to run our program again using ltrace and encrypt, we're able to see that, oh, voila, there's some weird shit that happened. So we're able to see that we have, because of the existence of our flag, a file called flag, we have now been able to generate this file. And that means it read the flag that we presented it, and then it ran other different functions, used a rant, and was able to exit. It was able to close successfully. And we also see that there is a write to a flag called encrypt. So that's basically a dummy test. So we're using LTRS to look at the library calls that are being made, and we can see that now the file actually executes correctly because we have this thing called flag. If we're to remove our flag in this case and then run the program again, we come back to just a minute. Yep, we get back to our segmentation fault. So this having this specific file in this case is basically one of the things that we're basically now looking at the process. We understood that one, we need to run, if I to run this program, we need an input, and that is basically what is being given. So if I to look at the description of our challenge, we're looking at challenge description. Our regular checkups of our flags, our secret flag storage server were found out that they were hit by ransomware. The original flag data that is nowhere to be found. The original flag data is nowhere to be found. But luckily, we not only have the encrypted file, but also the encryption program itself. So in this case, we have going back to reset what we need. We can just remove the flag. We can remove flag and encrypt, and maybe even encrypt one. Yeah, so we can just copy flag back, and then remove flag. Yeah. So we reset back to where we were. So simple description of our thing, of our challenge. So we have our encrypted file. If we were to look at it, basically it's that. So yeah, so we have a breakdown basically. If we're using hexdump, we have this is how basically we're looking at this at a low level. You get, and this is a conversion, of course, at a hexadecimal level because some of these things we cannot read them. But this is what our flag looks like at a hex level. So we want to be able to get what the flag was in this case. So now that's when we go through the process. The screen is visible. I'm not seeing the screen. Okay. Guys, don't confuse me. This is a moment of thought. you finish all my battery. So so now when we go to, of course, now breaking down to understand that how can we look at understanding the logic, because we are supposed to, but we also have the encryption program, so we need to understand the encryption. So we have R2, which is right there, and we can do analysis. If you do over analysis, it ask you that, hey man, we fired the R2 developer that we're heading to your location to analyze your binary. Yeah, it's just a dummy, just tell you that, man, you're asking overkill. So we can you just do ask analysis, and you can see that this has analyzed all the symbols, all the imports, entry points. Okay, so you have tools like, okay, what's happening? Okay, so we have like AFL, basically you probably dig in to give us visibility. As you can see, we are able to see some of the functions we're using: fopen, fwrite, fruntime. These are differently imported symbols. And then we have our entry point into the program execution, and then we have our main function. So of course we have to target our main main, because we want to understand and break it down. So just allow me run this one more time to get some clear syntax. So confirm you can see my screen, right? So you can be able to go. So the different things that we're explaining, just I ain't understanding. Michael, what aren't you understanding? We're basically just decompiling the program to understand what the logic is, to understand what was happening when we're running the program. This is basically what we look at as static analysis, because we have dynamic analysis where we're running LTRS to look at how the program is executing, what function it's calling. Now, at this level, we're not executing anything. We're just doing analysis using a tool called Radea. And Radea basically looks at decompiling. We can look at it. It can decompile for you different executables in different formats. For example, you can maybe say uh, you can look at this at a low level. For example, if you're very good with low level, this is of course looking at a C-like equivalent of your program. You understand? So we're looking at like how would it probably be written in C, but of course with consideration of the different registers. So are you working on a file? Isaac, maybe you can help me with Michael. Yeah, so this would be like the C equivalent. When you're writing your C code, you probably have like int main, then of course your different arguments, and then you of course declare your variables or etc. etc. Then of course you can call your different functions. So we have this is at a low level. This is an assembler. Yeah, this is an assembler breakdown of the creation of the stack. Then of course string the file is read. This is basically what you'll probably learn when you're breaking down your when you of course get deep into some of these things. So the easiest way I would look at it is from like a C equivalent, because this will give you at least some visibility. This is not, remember, this is not a one-on-one. This is not a one-on-one correlation with the actual code, but it gives you if you remember what we talked about how what is lost during the forward engineering process. You'll find that what is lost normally is the actual logic to how a program is basically executed, but as written by the developer, because the computers will understand the logic differently and implement it in a more optimized way, and hence basically what we're seeing here. So Radea is basically decompiling this ELF so that we can be able to see what is happening from a point of no execution, basically, as what look at what we're calling the static analysis. So this is, at this point, we are running an analysis to a C level. We're trying to decompile and get the syntax of the main function visible to us as the users, as like, for example, as like C code, you get. So that's basically where we have reached. So and remember guys, you don't have to understand everything. You don't have to any tool being launched. Oh, the tool is called Radea, guys. The tool is called Radea. Radea Core, maybe if you're just interested, it has a whole con behind it. So this is called Radea. There are other tools that you probably be curious about. You can just go here, Joshua. Let me save you the trouble of it. Now I've lost my mouse. Okay. You can just probably, yeah, you can just get to read some of these things. I don't think it's rocket science. Just dig in, crash your head a bit. Yeah, you get there. So in this case, we of course have different functions that we call fopen, ftail, fseek, fmalloc. Basically, this is memory allocation at the heap level, fclose, then of course srand. There's also time. So you notice, of course, then of course we have fopen again, but of course in this case we are looking at there is writing. So basically this is file creation. So this is file creation, and then of course we are also looking at this point here is file read, right? So that is the basic understanding. From what you can see, the file is a file called flag is opened. It is encrypted. It is read. It is manipulated using some algorithm here, and then polar flag.enc is coming out as the output. That is a simple breakdown of now the functionality that we've understood, that it takes something in and spits something out. Now we understand that what goes in within it that basically allows us to be able to what to of course understand what exactly is happening. Allow me, give me 1 second. Do you want us to take a small break? Take maybe like a 5-minute break so that everyone is aligned, and then maybe we can resume. Is that okay? Because I've been told that we're going up to midday, so probably, yeah. Can we take a 5 minute break? And during this 5 minute break, guys, I want you guys to shoot. I just want us to shoot if you have any questions, because it's, for me, I find it very important that you understand the what basically what we're going through, and then yeah, we can proceed. And also maybe Alice, we are doing reverse engineering practically. So yeah, yeah. Anyway, actually, this is a small challenge, so it's a very easy challenge, but I'm trying to make it as easy as possible for everyone to understand, because I could just probably just go ahead and do it, but that's not, it defeats the purpose of this engagement in a platform. Okay, it's interesting. Give me 1 second. Okay, we are back. Okay, Michael, for easy understanding, could we started from the sky? Well, I was given that this is an introduction class. I don't know. Okay, practical challenge. Can I finish this? Then maybe we can see how to go about that. And yeah, maybe just go through. Then yeah, because it's not good to start things and don't finish them. It's not a good thing. So so basically, I was showing you right there. But of course, I know also there are other tools that you can use. One of the tools that maybe I know that you'll also get familiar with at a Windows level is called IDA. Um, IDA is a very interesting tool. Let me first load the binary on the side so that there's some sensitive information that's protected. I don't want you guys to access study. Okay, so you load, of course, your binary into IDA. It's looking at this, it's doing analysis. So IDA is basically another tool that you can use. It's a tool by X-rays. It gives you analysis. So you just load your binary, in this case, ELF, and you can be able to. It can be able to look at now. Now this gives you a breakdown of how basically your program is run. So Same things. We have fopen basically, which is fseek, malloc, reading, srun. Then we have, of course, there is a check here. In this case, we have an output that comes out, and then we have a stuck check fail, and then of course we have what? We have this close that happens. So this is basically the program logic from a graphical point of view. So we have our main function here. Remember, we also have our start, basically that looks at how our logic starts. So with this tool also, you can be able to do like different things. It gives you visibility onto how the different functions are being called, how, for example, how your execution, your algorithm flow basically also moves. And yeah, that's mainly where we shall start from. So when, for example, we're doing, because I think Radea is too, you complained and I've heard you. So when we look at, for example, these these functions here, and we look at between what you look at as this part, we look at fopen, fwrite, and then fclose, right? So the first thing we can probably do is that we need to understand how the flag basically how the logic of the flag sits, you get, in terms of what is used, what functions are used. If you remember last time we talked about XOR. As you can see here, we have XOR that is being used, and these are things that we need to align in terms of the logic flow. So when you're understanding, for example, reverse engineering, you need to be able to understand that, for example, what does this mean? What does this mean? What do these different symbols basically, what do they mean? So you need to understand that we have, of course, when we are calling, like for example, a function, we have, of course, different arguments that it takes, and depending how they are set up, we had ESI, and of course EDI. Basically, this is how we're setting these things up when we're looking at the x86. But given that this program is it's a 64 bit program, we have, of course, RSI and RDI, and these are the parameters that basically these are the arguments that fopen is going to take. So with the low level, what happens is you first create you first get that function, you set up the different arguments, and then of course the calling function to be able to take in this logic, and then the same thing keeps happening for all the different functions. So like for example, malloc, we have, of course, the RDI taking up, and then of course we also have what RAX basically that's taking up the the reference of what RBP and size basically this padding is showing. So it's the same logic when you're going to, like for example, at a low level. So once you understand what these different registers are used for, so the registers RDI and RDI, ESI, RDI, EDI are all used basically to carry different arguments for different functions. Then we have EAX basically, which is the return it carries normally what you're calling back out of a specific function. So then we have RCX, which is, I think, the accumulator. Basically, when you're running counts and all those things, that is basically how you'd understand them, and you use that logic to basically understand how the application is basically loading in terms of data from memory and maybe into the different registers, whether the register is being called in terms of, like, if I have, like for example, these brackets, and when I just have, for example, just a register, there's a difference because there's a pointer that is involved to actually point at what this is carrying and moving it to RX. So those are like the small nitty-gritties that probably you need to understand. So when we go to reverse engineering our algorithm, the first thing that we probably need to pay attention is we've understood the syntax. We've looked at how this is basically reading. This is what's opening. Then we're looking at this bit. So once we come here, we look at one, this is what we're looking at as the low level side. So this is also another tool, as I said, that you can use. There's also another one that you can use. There is Kata, which is basically Radea's graphical user interface, and this also gives you the visibility. So to go into conclusion, because I want to solve this in the next 10 minutes, when we come to C, because the C equivalent basically gives you at least a small understanding of what's happening. You look at one, you look at understanding that, okay, if I'm to break this down to the right, if we're to hex dump our flag, we can see this is our flag, the flag that we're looking at, right? And we are seeing 5A blah 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 blah. This is how it's basically being looked at. So there are ways that you can look at working back. For example, you can look at you can take in this flag, and then you work the algorithm backwards to be able to give you visibility onto what exactly is being built. So if, for example, I'm to say normally how reverse engineer something that is interesting. For example, I don't want us to use, let me just give you a scenario. Let's copy a flag. This flag. If I'm to say, like, for example, echo, let's just say a 5 is, maybe say 4 is 1, 2, 3, 4. And maybe say I'm to run encrypt, right? I'll have my flag encrypt. But if you now notice, basically when we had our AAA, yeah, we have basically gotten an output that is this, right? And if, for example, we removed, let's say we remove the flag.enc and then run it again. I normally tell people, like, some of these things you need to be able to be very practical. And then we run our check again, and then we see. Do you notice that the flag has changed but with the same input? You notice that the flag has changed but with the same input. So there is basically randomization that is happening, and we're using a very interesting function that we look at. In this case, we have srand, here, and basically these are things that you notice. So with this specific flag, I have sent the output. I've sent this flag again, but if you notice that our output is different. Do you guys see that? Hello? Okay. So you understand. So you're asking yourself, like, how can I use the same thing and basically I'm getting something that is different? Like, it's like, for example, I give you chapati and maybe and eggs, and then, man, you make me a Rolex. Then again, I give you chapati and eggs, and then you make for me, like, I don't know, I don't know whether you guys used to have serious combinations, but like you have a serious combination that you know that you implement. It becomes very interesting because you're like, what is this, right? So they're of course different. This is basically the breakdown of how you understand. So you look at, okay, I need to understand that, one, what is my what exactly is happening in terms of what the logic. So we have malloc in use, we have malloc, we have time, and srand. And these are the functions that you need to, like, pay attention to. Exactly, like, what are they doing? Like, what are they trying to, like, do? Because when you look at, for example, your algorithm here, when you come here, there is this interesting if. Do you guys see this if function here? We have, when we open our file, encrypt, we set up the stack, then it's first of all a check if, then it will give you somewhere to go to return. So if you remember, when you look at this, when you go to, if this is not equals this, go to lock zero thing, which is basically this, which is our stack check. Yes. Then if that means if a file exists, if the file doesn't exist, the logic will fail. Then after that, if it doesn't, if this check passes, then we are going to proceed and go to this 001.143, which is basically let me say shop location. This is 00, so go to so unlikely, go to 143 C 143 C. So 143 C. So just a minute. 143 C location. We have this. So we have our string opened encryption. Then we have our right of the flag, stack canary, then 143. Then we run and return. This is our return. Okay. So once we able to understand the logic, we start looking at, okay, there is an XOR here. There's an XOR. This is for our canary checks, if you know very well how we are setting up. So we look at one, what these different ESI, EXI, and F right. Then we're looking at basically the logic of the algorithm. So we know like that this is like a for loop. This is like a for loop with, of course, an initializing factor of like this our like the first value that we're looking at, the one that initialized is going to be equivalent to what, like 4. So it's basically trying to define what we're trying to understand is that if we have our XOR that is in use, we have our XOR. If we go back to how the breakdown comes also to do with, because you can see XOR more clearly when we're looking at this. We have jump to this. We have our XOR in use here, as you can see on our logic, and we have, of course, with run. So here, basically, you can see at a low level that this is our algorithm here that is doing that chaos. We have addition, blah blah blah. This is the breaking down of the arch algorithm. So to give you something that this equivalent, for example, if you want to understand, one thing is I'm giving you all the tools that you probably need to use for you to be able to understand these things at a low level. Because if, for example, if one tool is not working for you, some tools work with specific files, some work with other types of files, and okay, okay. So yeah, so this is basically what we look at as we have, of course, our our code at a C level, but we also have a very powerful tool that I normally use. This is like it's like the undercover agent that I use. I don't know whether I have it installed here, but you guys pray for me just to show you guys. We have another called Gidra. I don't think we have Gidra here. Gidra is also another interesting tool. Maybe I can just show it just for knowledge purposes. We have another tool called Gidra. And Gidra basically is, have you guys heard about Gidra? Gidra is also, this is one of like, I don't think this is the right page for giving out Gidra. But yeah, Gidra is one of those tools that was developed by NSA. It's very, very good at low level, and it can also give you basically the C equivalent. This is basically what it is, and it's very chaotic. It's very difficult to learn, but of course, it's also one of the best tools that you can actually do. So our process is decompile, debug, understand the algorithm, reverse engineer the algorithm, because you need to be able to you need to be able to you need to be able to like you need to be understand the encryption algorithm. So when you now go to analyze our algorithm, in this case, when we go to how we're looking at where is our FTL from here, this is where the chaos is. This is where our chaos is. And we look at when we're looking at that, the first thing that we have to notice that, of course, here we open the flag, we are reading, and then of course we use fseek. We have fseek that is in use here. You get, and we have basically fseek that is implemented, and then we of course go and create malloc. So we are creating an argument basically that is going to be used by malloc. You get, and then there's going to be a file. Of course, there's going to be malloc normally creates, of course, memory, in this case, like a block of memory, and we have to make the assumption that that is going to be equivalent to the size of what, of our flag, and then it allocates the memory space for it. So once the file is, once you look at, we go all the way and we have this, basically we have this closed, right? So once we have this closed, then we start seeing that there is creation of a seed in terms of time for srand. You get, and its return basically, this is, as you can see here, this is our seed. This is our seed that is created for our srand. You get, so basically what's happening is we are randomizing whatever logic we are basically created, that we created, the what, that we're able to save onto what, onto that we're able to write onto the heap using malloc. And we of course, now this is what is causing the randomization within on our flags because of this specific um, function. So once this happens, we look at how now we can go about it. So from basically from the graphical point of view, to just give you just a recap, you look at it, then we have, we can see that we have around here, right? So we have this, we have a check. We either go to this, then this happens over a given period of time. If you can see, this is a loop, like it goes, do you see this? It comes, this is your logic comes, we come to a point. This is where we do the file creation from. This is where the category is happening. So we have of course our run. So it's called once, second time, then we go, and this process goes, does this, then does a check. So this is like a loop. This is our loop here, for which we are going to, once we are done with our loop, if it meets this parameter, this check here, there's a comparison between the size of, there's a size of in this case what we have within the heap and rdx. If the size is the same, if we have jump, this is a jump, we have equals or not. So this is, we'll have it coming to this or to this. If this parameter is not met, if this check is not met, then we're going to have this, us moving to this rather. And if this condition is met, yes, if Rx is the size of Rx is going to be the same as this output, then we are going to come and write our output basically to a file, and this is what we get as, this is what we exit. Does that make sense? That is why I wanted to use as many tools as possible to break down for you to understand that that is the actual, what you're seeing at a low level is basically just some category in terms of like like the terminal can confuse you and you start thinking that maybe it's rocket science, but this is just a simple breakdown of how the algorithm works. So it gets something, it does randomization around it, uh, keeps adding values, confirming that the size, if the size matches what is basically within this, then of course it goes ahead and what, and 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 saves the file. And that is all that this program, as simple as is. So let's go down to writing code that can reverse engineer this, basically this algorithm, so that we can be able to conclude. So dang, bro, this is introduction to reverse engineering. But okay, okay, is this too much? Maybe if it's Artisan, just calm down. What's wrong with you? So actually, I won't lie to you guys. For me, I was told that you guys already covers the basics. So like the introductory basics. So yeah, but yeah. If there are any questions, guys, feel free to reach out to uh, Joel, the team. Yeah, and then maybe we can, if there are any things that are missing, then yeah, like this is introduction, guys. If there is any need for maybe any clarity, capture a moment, take notes, feel. You guys are scaring me, making me feel like I'm a very bad teacher. Wow, this is interesting. Do you guys want maybe to take a break? Maybe just ask any questions, then maybe we can continue. Is that okay? Is that okay, guys? Maybe. Yeah. Okay. Gone wrong? I don't think it has gone wrong. Maybe just if it's too much, maybe I can just go and explain something else that is very small, then like maybe low level, because I don't want to feel like I'm overwhelming someone. Yakatandika. Okay. Let me give me. Okay. Okay. Just give me a question. Give me one. Give me 1 second. Okay. Open my brains. I don't know about the feedback. If there's anyone understanding, even if it's just one person, I'm gonna go ahead finish, and then we can do. Yeah, because I don't want to feel like those guys who leave things halfway. But this is basically just that's why I use different tools to be able to give you visibility. Don't the tool is the last thing on the chain. The most important thing is you as a person. And good, thank you, Nicholas. And basically, what you need to understand is that this, like this way someone said, reverse engineering. What's the difference between the reverse engineering and binary exploitation? They're almost the same. But of course, like now when you look at binary exploitation and reverse engineering, they're like sisters. For us now, we are reversing. You can reverse engineer anything. Maybe just to give clarity. Maybe we chose a bad example for the class in terms of what you probably expect, because yeah, that's basically what we have. And this is a very simple challenge actually to understand when you're breaking it down from a point of experience. But when you're looking at the difference between binary exploitation and reverse engineering, when you're cracking software, for example, um, your software that is cracked is basically reverse engineered. Someone writes a script that maybe breaks or patches that executable to allow maybe a specific person to run software without a license. Maybe, for example, you find that at a code level there is a check. Like for example, if a license is uploaded, grant access to the solution. Then there's a small check. If someone just switched, if license is not accorded, continue and give. So someone goes a low level, understands that logic, maybe patches it, maybe by overwriting a specific register. And remember, this is code level. Logic is like, for example, where I have a jump, like let me say where I have a jump, like for example here, yeah. This is can be like jump if not equal, jump if equal. If something here is saying jump, uh, for example, we have maybe say this is a jump that's happening. So this jump is checking for, it's going one way. If there is a condition here, like for example, as you've seen here, there's a condition that checks. Yeah, there's a condition that checks, and if that condition is reversed, then we get the what, the opposite, and that we shall be breaking the application. We shall be breaking the application logic. That is basically what reverse engineering is like. And reverse engineering allows you to do so much stuff, understand at a low level. Binary exploitation, you look at, do I have my binary? Maybe I want to exploit a specific vulnerability. Maybe if it's a memory-based vulnerability, in this case, if the security is not well done right, you have control. You input maybe some malicious payload that you may be inputting that within to the binary, and then you're able to achieve specific exploits at a binary level. So yeah, do we exploit binaries before we reverse? Guys, it's not just about this. This is an open discussion. Yes, like reverse engineering is anything. You can reverse engineer a process. You can reverse engineer an application. You can reverse engineer so many different things. So it's just about what the end goal is. Like for example, even like when you look at the different um, like how should I look at, like most of the tools that are written, they take advantage of specific loopholes at a protocol level. But how did those people understand how to write those specific things? They reverse engineer those applications to be able to understand that at a specific point in execution, if I can overwrite this specific memory address with maybe this specific issue, yeah, then I can be able to achieve this specific functionality. So that's just the logic. So I think that is the best the best explanation that I can use to maybe like just break it down. I don't know, does that make sense? Because I feel like I'm over explaining and not getting anything done. So it becomes very scary. I'm like, what? Yeah. So I think one of the best tools best explain for you is would be Gidra. Because Gidra, for me, I think it's of all these tools, you see how, for example, IDA was able to break it down for you. Now, NSA built one of the best tools that you can have here. We have another tool called Gidra. This is Gidra, and Gidra, of course, is for me, I think it is like the one guy that you probably would need. I don't know whether I can install it directly anymore. Let me see. Oh, okay. So it looks like I'm having breakings. Okay, as that happens in the background. Um, Let me just check your chat just to confirm we are together. Could you please take us through the oh, okay. Then got saturated. Guys, this is not rocket science. Just breathe in, breathe out. You need to take a walk a bit, take a walk, just but don't overthink about it because guys, this is like I think you're the most advanced class we've had so far in the years, and we appreciate you guys for giving us your time to try and share the little we have. So we, in the same spirit, we want to ensure that everyone is understanding everything, and yeah, it's basically just as simple as that. So so basically that is. So can we now go to understanding how we are going to work this out? I want to solve Hydra. When Hydra is done, then we can start working backwards. Yeah. Because the logic is so interesting, right? So we want to be understand because now when we're understanding this thing, the first thing we need to understand is we need to be able to read our encrypted file. Then once we've read our encrypted file, we have to of course we have to get the size, the file size, because those are the checks that are being done. Those are the checks that are being done. Because once you look at this algorithm here, we read, right? But we need to confirm the size. You get. So once we get the size, then of course there now we have to get a seed, and then we read our encrypted data. You get. Then we go through the logic that basically we're going to go through. And if you realize what was happening is when we're using IDA was we see that this is a value at 7. Yeah. So we have this specific check. So this is a condition. So we have random first the first time with this this we have this AL register, and when you look at this, in this case we're having EX basically, which is an and equivalent of 7. So we add this and push it to EX, and it's what we put and serve all the way to our, this is on our second randomization. So we have two runs that are running through in a loop form. Once we confirm the size, because size is our check, then we can be able to write. So working backwards, we would say, okay, can we, since we have our flag, then we work backwards, 1, 2, 3, while comparing the size. When we compare the size, once able to map this, then we can do this comparison and go back all the way to flag. That is now, this is the process now look at. This is the forward engineering all the way up to this endpoint. And then from endpoint, which is basically this, going backwards all the way to flag is basically how we are going to be able to reverse engineer. So yeah, let's go ahead and maybe write some code and yeah, see how far it goes. So I've already done this program before so many times, and yeah, I can maybe just give okay, as Hydra installed. Don't help me break. I hope I don't break my machine at this point. Any questions at this point? Okay, so let me just go to security. Are we together, guys? So are we together? So the machines are breaking. Let's see, guys. So yeah, I guess what is lacking the understanding hard is the register operations, understanding the function stacks and operations. I don't really think that is okay. Maybe yeah, maybe. How many of you guys have a programming background, if I may ask? By a show of, I don't know. I. Where is the current? Okay, Moses, shoot. Moses, you're free to speak, guys. Don't feel like the world is breaking down. So, hello, hello. Okay. So maybe just to break it down, just make it simple as much as you can. I'm losing track of you guys. Moses raised a hand. Was this just for sure? What's up? Okay. So basically to make it easy, because I kind of want to save us time and also to just give you a read, because this is just something we've already done in the past, and yeah, we have. I'm going to basically just, so we have what we call decryptions C. This is basically just a script that we're going to use to look at how the logic basically works and looking at the checks. So this is a script. basically to reverse engineer our algorithm and to break down how basically we will do this. So if we look at our C equivalent here, this is C. I want to install Ghidra, just Ghidra, please install. If it breaks, then I don't know what we're doing. Okay, good. Okay. We have 50 minutes, 60 minutes to do this. This is a moment for you. You asked what to install the program. That's why. Oh, nice. Sorry, Moses. Thank you. My bad. I'm a village man, so sometimes these technology things are really dangerous. So yeah. So someone asked Ghidra. Ghidra is actually one of the best tools, and as long as you guys have a good programming background, and guys, don't think about this as programming. Remember, you're building this in teams, and yeah, today we've installed Ghidra. Wow, there's already an argument. Close. They already have exceptions, but let's try and see. New project, unshared, next on, cyber stars rising. Finish. So, cyber stars. This is a tool for analysis. So we have different components can open. Mhm, mhm. This is our project program. So the beauty about all these things is we have encryption. So this is Ghidra. It does not didn't have the best UI, but it's one of the most powerful tools I know out there. So yeah, it's a demon on steroids. Have I done the wrong thing? Uh, okay, so we're doing analysis. We're doing crazy analysis. Same things. Look at this. Look at this area here. So analysis is happening. This will be my PC. My PC may hang. Dang. Okay, but yeah. So as it does the analysis, you're seeing here, it's looking for strings. If you guys remember the process that we're doing, we're running looking for strings. Then after that, what else did we do? Understanding the file type. You saw basically what it did. It asked it file type. You look at the sections. My PC has frozen a bit, guys. The VM is crashing. Don't give me. This is like the worst thing ever. But okay. So as this works, guys, I can't work. Are you seeing this? This is interesting. We are dead. Did I just kill myself in the presentation? Okay. Whoever asked me to install Ghidra, you guys have killed me. Oh, God. I'm dead. I'm so dead. Are you guys seeing that? Like, wow. All right. It's fine. Don't worry. We shall. Yeah, yeah. It had to kill itself. Just a moment. Unresolved. Uh, guys, these emojis are funny, by the way. When you guys send them, it's like this. He gain you regard. Bro, what are you doing, man? Don't kill me. Yeah. So let me just get the terminal and just kill the process, as we said. So yeah. So maybe just to break down as this thing does its, I just need to get some access to the terminal. Okay. And Uganda in headless mode. Uh, so the demons of Kabuki have come to take over. Jesus. This is interesting. Spike, spike, spike. Good. Close. Uh, huh. Are you guys seeing how dead I was? But I think the village guys have come soon. Yep. Okay. Uh, bro, there's no way. Hey, man. Let's close this. I had a feeling. So we are back. The analysis is done. Guys, don't install Gidra on your machines if you're not ready to suffer. So, wow, that's gonna be embarrassing. So of course now here we see you have functions as the same breakdown. We have imported symbols. Our interpreter is the shared library. Then of course exports. So when you look at this specific interesting bit, this is like where we get the interesting functionality. Um, this is now where we look at the most interesting bit. So when we are to say, for example, start, you guys notice this. Actually, this is this chaos that you guys are thinking about. Forget about it. This is now where we pay attention to. libc start. This is loading, of course, shared object. Libc, and we go to main, right? So when you look at main, this is the actual logic, as simple as is. This is the actual logic. We have our flag. Do you guys see now how Gidra breaks down this simple thing that we've been trying to look at registers, to get chaotic, blah, 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 all these things. And yet it just gives you a C equivalent. You have fseek, fseek, fmit, fclose, then time set, our srand. Then we take, of course, on Segunda seed, we have initialize the first round, then this, then we have an and check with 7, and then we have to right shift left shift push bytes and right shift push bytes. Now these are maybe things that maybe I need to explain also to some extent, because for example we have a left shift and a right shift. These are very interesting concepts. Maybe I can just break them down before I give you the final solution. When we are, for example, looking at when we're looking at shifts, I don't know whether they can I shift in Python. Let me see. 100, it is 100. Yeah, so if I'm to look at the binary of 100, you see, for example, and let me say the binary of 100, shift 2. Do you notice that the length of this, which will remove these two, uh, two values, these two zeros, and we're just left with this. So when we're shifting twice, we're basically moving this thing to the right and pushing out whatever right shift. We're pushing out two guys. When we're pushing this to the right, we push out these two guys. When we're pushing this to the left, for example, if we'd say being 100, guys, I think these ones you have to go and learn them yourself. When we push, we're pushing this towards the what? Towards the left. So we add there two zeros. Does that make sense? Yeah. At a binary, does that make sense? Yeah. So we have this small check, this validation that is done, that we're shifting 8 and we're shifting basically to another s byte. In this case, when we're looking at this s byte, basically just an argument that we can rename and maybe call it I in this case. So this is, you can see that I is basically initialized from this point, then it does an AND 7, and then basically it's the one that is what being used in this algorithm. Understand? You can also take up maybe sounds. You can do the renaming, just make a code look like something that you would get out of a telenovela. So basically what we're doing is we have this read that happens, we capture this time, and then now this is like, now for example I can convert this also to J so that the code doesn't look like it's from some alien space. So we have F. So basically now you're seeing that our code is starting to look like something that would probably work with. So I already have, of course, the decryption script for this, and to give maybe clarity, as we can maybe break it down in terms of explanation, if I'm to look at, for example, in decrypt, let's see, we're just basically reversing what we're doing, what we're seeing with our 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 algorithm here. So uh, we have uh, an and of a shift to the right, a shift to the what? To the left, and a shift to the right by 8. So we do the same thing. We shift to the what? We shift back. We get our we get our encryption file, and then of course we set it up for we generate the random seed. Then of course now we start considering the what? The length, as you can see with our same algorithm. So this is how interesting when you're looking at working backwards. It's just you get this algorithm and you work backwards. This is where the logic is. As I said, it's very simple, and basically all you have to do is once you understood, you first start by creating your random variables. In this case, initializing. Remember, you had round one, and round two, as you can see. Then from there, we go ahead, run this first, then run this second, then go take the loop backwards. Once the check confirms, in this case, we're looking at this. We're looking at the size check in this case. Once the size aligns, it tops, and then we're able to what? To write into flag. So with that, I don't know whether that was easy to explain. We can use this C decrypt.c solved it. Can just say solve. So if I'm to say, for example, we must make a new file, solution of, so if I have like, for example, in this case, remember we had move flag.encrypt here. So if you remember our hex dump was C, the flag, we had this was our check, right? And we were able, so if we were to say let's read our flag, in this case flag.encrypt, that's what we're calling it, and then we run our solve. Let's run ltrace while writing our solve. We're able to, of course, run the same checks, we're able to read our flag, run our algorithm, in this case the randomization, and write our output. And you can see that this is our output. So once we say let's read flag, we're able to get our same what? Our same output, the one that we randomized. And remember, as we had said, hex dump, see, flag.enc is a random value. And even if we said, okay, let's maybe say, let's maybe say remove flag, and in this case we're going to so in case maybe say we're going to say echo, this is the last thing in this challenge. Well done guys. So I have done the no error. Well done guys. Let's say this is our flag. So if we're to run encrypt with our flag, let's first remove that argument, just my mistake. Encrypt, we have our output, which is flag.enc, as you can see. C flag.enc, we can see that is a random thing. If we're to say, if we're to remove flag, then we have to copy, or to move, or copy in this case, move flag, and we see this is our same file, right? So if we run our solution, So just validation, we can run this, and when we run flag, in this case, we're able to see that this is basically the same input that we had when we were creating to our flag, which is what has come out of our algorithm. So that is basically just a simple reverse engineering for a binary, and basically understanding this. When you ask me about binary exploitation, there's a very interesting thing at the front of my mind. You see, reverse engineering requires you to be able to beat the algorithm in terms of it can require an input and an output. Exploitation, binary exploitation can focus on actually bypassing controls. You get, for example, if I've locked a door and I want to introduce maybe to implement, like, maybe say, for example, I have a specific function that I want to call. You get, I can exploit the binary to call that specific, to do what, basically to manipulate the binary to do what it's not designed to do. That is basically why we're looking at binary exploitation. Reverse engineering is majorly around understanding or breaking the algorithm, and finding out how the thing was engineered. So basically that is a breakdown of my very simple challenge. At this point, I'm very open to any questions, and yeah. Did you guys enjoy Gidra? I think Gidra broke down everything for you guys, just made your life easy. So my recommendations to you guys would be probably go out. There are some sites you can use. You see all these things that I've been showing you. Don't even sweat. Don't think a lot. Don't feel like the world is about to end and you're going to go back to Kumi like me. Just go and search for something called Pond College. Huh? Pond College. It's a very interesting area. Michael, I don't know about time, but I'm actually going to be creating for you guys some challenges this week. And unfortunately, I have gotten an emergency in terms of work, so I have to drop off immediately. But for your personal reach out, you can reach out personally in the evening. I could probably just I can talk to Joel, and then maybe you guys can present maybe some specific challenges that you have that are difficult, and then maybe we can walk through them. I need to break some of these things. Just allow me. How was the session? If you guys were to give me a rating, uh, sometimes this feedback is very important for. My WhatsApp is available through Joel. You can reach out to Joel. I'm in the group. I think everyone is in the group. I'm in the group. You can just find me by my alias, Great One. And yeah, that is one of the first things I think I had stated. So with that, I would like to conclude. I hope the session was informative, and wishing you guys a lovely weekend. Cheers.